Have you ever, stopped to think about how much AI is growing?
Growing? You mean like its capabilities?
Well, yeah, that too, but I'm talking about the sheer size of these things. AI models, they're getting huge EE, like billions of parameters.
Oh, absolutely. Like those transformer models, right?
Yeah.
6 billion. With a B.
It's mind-blowing. But here's the thing. I was reading that these models are getting so big, they won't even FIT on a single chip anymore.
You're exactly right. We're kind of hitting a wall. Not a wall of ideas, mind you, but a wall of what our hardware can handle.
It's like trying to stuff, I don't know, a giant octopus into a teacup. So, how do you even begin to train something that massive?
That is the challenge, isn't it?
Yeah.
And that's precisely where GPipe comes in.
GPipe. Okay, so is that like some kind of supercomputer?
Well, you could think of it that way, but it's less about brute force and more about elegant engineering. Imagine, if you will, a factory assembly line.
Okay, I'm picturing it.
But instead of cars, we've got data flowing through. And each station on that line, that's a powerful computer chip, a GPU.
So instead of one massive machine, it's broken down, right?
Exactly. We break the model and the data into smaller pieces. These smaller chunks of data, by the way, those are called micro batches.
Micro batches, gotcha. So each GPU works on one of those.
Precisely. It does its part of the training, then passes the work along to the next one. Much more efficient use of memory.
Makes sense. But these papers I was looking at, they mentioned cells and partitions. Where do those fit into our factory picture?
Good question. Think of cells as the stages in our assembly line. Each cell handles a specific part of the model.
And partitions?
Partitions are even finer-grained divisions within each cell.
Okay, so it's like really, really broken down.
It is. And to make everything even more efficient, GPipe uses something called rematerialization. Basically, instead of keeping every single component on hand at all times, it's like we only keep the tools we need at that station. Once they're used, we clear them away.
So it's like a, what do you call that, just-in-time, like a just-in-time AI factory.
Chuckles.
Okay, but can it handle different kinds of AI models? Or is it limited to just, one specific type?
That's one of the best parts. GPipe is incredibly flexible. It's not limited to a single type of model at all. It can handle convolutional neural networks. Those are CNNs.
Like they used for their AmoebaNet, right? For image recognition?
Right. Or transformers, which are fantastic for language processing. Pretty much anything you can break down into sequential steps.
Wow. So it's like having a universal AI training machine.
You could say that.
That's wild. But with all these different GPUs, all these stations in the factory, how do you make sure they're all working together correctly?
Another good question. It all comes down to something called synchronous gradient descent.
Synchronous gradient. Okay, can you...
Imagine each worker on your assembly line has to synchronize their watches at the end of each step.
Okay.
That's essentially what synchronous gradient descent does. It makes sure all the GPUs are on the same page during training. Leads to much more reliable results.
Okay, so we've built this incredible AI factory, right, with GPipe. But what can it actually build? What kind of AI models are we talking about?
Well, let's start with something kind of basic, image recognition. The researchers, they used GPipe to train a massive AmoebaNet model. They trained it on ImageNet.
ImageNet, what is that, like a database of images?
Yeah, think of it as the ultimate test for image recognition. This AmoebaNet model they used, it had 557 million parameters.
Okay, so we are talking some serious AI brain power here.
Absolutely. And it managed to achieve, get this, 84.4% top 1 accuracy on ImageNet.
Okay, but for those of us who don't speak, AI stats every day, what does that actually mean?
Basically, your phone could recognize thousands of different objects in pictures and be right most of the time.
Okay, that's actually really impressive, but image recognition's one thing, right? What about language? Can GPipe handle that too?
Oh, absolutely. In fact, they used GPipe to train a single AI model for multilingual machine translation.
Wait, hold on. A single model that can handle multiple languages? How many are we even talking about?
Over 100.
You're kidding?
Nope. And this model, this one model, had 6 billion parameters.
6 billion. There aren't even that many people on Earth.
It's wild, right? And here's the thing. This single model, it often did better than individually trained models.
So you're telling me one AI could potentially handle translation for over 100 languages and do it better than one specifically made for each one?
Especially for languages with less existing data to learn from, yeah.
That kind of blows my mind.
It really makes you think about how AI learns, how it understands language in a different way.
Okay, so back to GPipe for a sec. training these huge model, even with this pipeline thing,
Yeah.
that can't be easy, right? What kind of challenges did the researchers have to overcome?
Oh, there were definitely some hurdles. Training at that scale, it's tough. One of the big ones is just maintaining stability. Imagine you're building a tower, right? The taller it gets.
The more unstable.
Exactly. Same with AI models. More layers, more sensitive, more prone to errors.
So how do you stop these, like, AI towers from tipping over during training?
They had to get clever. One thing they did was scale down the initialization of some layers. Basically, they start with a stronger foundation.
Ah, so it's less likely to wobble when you're adding more on top.
Precisely. They also use a technique called clipping that keeps the model's predictions from getting too far out there during training.
So it's like, what, putting up guardrails, making sure the AI doesn't, like, veer off the road while it's learning.
Exactly.
Okay.
But even with all that, you still need a ton of data to train these models, right?
All right, gotta feed the beast.
Which brings us to batch size.
Yeah.
How many examples the model sees at once? The researchers were working with huge batch sizes, sometimes up to 4 million tokens.
4 million. That's like feeding the AI a whole library at once. Did that even work?
Surprisingly. Yeah, it did. Increasing the batch size actually led to some really significant improvements in accuracy and ED efficiency.
Huh. So sometimes more IS, more.
It can be, especially with these giant models. Of course, there are practical limits. You can't just keep increasing forever. But GPipe, with the way it distributes the work, it makes it much easier to experiment with those larger batch sizes.
Okay, so to be clear, GPipe helps us train these massive AIs, the powerful ones, but it's not the only game in town, right? What are some other ways to tackle this model parallelism thing?
Oh, for sure. GPipe is just one piece of the puzzle. There are other approaches out there, each with their own, pros and cons.
Like what?
Well, data parallelism, for one. That's a more common way to scale training.
Data parallelism. That rings a bell. Remind me how that one works again.
So instead of one big AI factory, picture multiple factories.
Okay, got multiple factors.
Each working on a different set of, whatever it is we're building. Cars, in our analogy. Each factory gets a copy Y of the whole model, but they're working with different chunks of the data.
So it's like divide and conquer for training.
Exactly. It's relatively simple to implement, and it works across a lot of different hardware setups. The thing is, though, it doesn't solve the problem of the model itself being too large for a single GPU.
Right, right. So it's great if you just need to, like, speed up the work. But if the AI is too big for the factory in the first place, you're still stuck.
Right.
So then how does GPipe compare to that? To data parallelism?
Actually, they work really well together. Think of it like this. Data parallelism, that gives you multiple factories. GPipe is what equips each of those factories with a super efficient assembly line.
Ah, okay. A 1-2 punch.
Precisely.
You mentioned other approaches too, though, right? For model parallelism, besides GPipe.
Yeah, there's Mesh TensorFlow, and then there's PipeDream. They both try to split the work up in different ways.
Okay, we touched on those a bit before, but could you refresh our memory? How do they actually work, and how do they stack up against GPipe?
Sure. So Mesh TensorFlow, that's all about breaking the model into even smaller pieces than GPipe does. Instead of pipelining whole chunks, it's like having specialized stations for attaching doors, tightening bolts, you name it. Very, very specialized.
So it's even more broken down than GPipe's approach. What's the advantage there?
If you can pull it off, it can be incredibly efficient. But you need really fast connections between your computer chips. Like, think super high-speed conveyor belts between all those specialized stations.
Ah, so you need top-of-the-line equipment to make it worthwhile.
Yeah, it's very reliant on having that hardware. That's one of the downsides. It's not as flexible as GPipe.
Gotcha. Super speed, but with some caveats. Okay. What about PipeDream? How does that one work?
PipeDream is more similar to GPipe, actually. It uses that pipeline approach, too.
Yeah.
But it's much more aggressive about how it schedules tasks. Tries to maximize efficiency by, interleaving the forward passes, the assembly steps, with the backward passes, are quality control checks.
Okay, that does sound pretty efficient. So what's the catch? There's gonna be a catch.
Lastus. The catch is something called weight staleness.
Wait, staleness. Is that like when your AI needs to go on a diet?
Not quite. See, because PipeDream updates the model's parameters asynchronously, meaning not all at the same time, there's this risk that some parts of the model might be working with outdated information.
Oh, okay. So it's like part of the factory is using yesterday's instructions while everyone else is on the updated version.
Exactly. And that can cause problems, obviously.
Yeah, no kidding. So GPipe's approach is better for that.
It can be. That's where it's more, let's say, conservative approach
Yeah.
with those synchronous updates that really makes a difference.
So maybe not as flashy or potentially as fast as Pipe Dream, but
But reliable. It avoids those weight staleness issues. And when you're dealing with models at this scale, reliability is absolutely crucial.
because one little mistake could snowball into something huge, I bet.
You got it.
This has been fascinating. We've covered a lot, from like the nuts and bolts of GPipe to the bigger picture of AI training. It's clearly not simple, this whole giant AI thing.
It's a challenge, definitely, but also an incredibly exciting area of research.
And we're just getting started, really. So, like, where do we even go from here? I mean, it's crazy. We went from those early AI models that could barely recognize a handwritten number to these massive systems that could translate over 100 languages. What's next? Now that we can train these giant AIs, what can we actually DO?
It really is remarkable, isn't it? And that's the big question, isn't it? GPipe, these other technologies we've been talking about, they're really opening up a whole new frontier in AI. We're finally getting to the point where we can tackle problems that before would have been, impossible, just completely out of reach.
Okay, so like what kind of impossible problems?
Well, imagine, for example, AI that can design like life-saving drugs, or I don't know, create a totally personalized education plan for every student,
Whoa.
or even just like help us understand the universe better.
Okay, those are some pretty big dreams. It sounds like we're on the verge of like a whole new era of AI-powered discovery. That's pretty exciting.
It is exciting.
Mm-hmm.
And it's not just about, these huge abstract problems, these advancements. They'll impact everyday life too. Imagine.
Mm-hmm.
No more language barriers. Like you could have a normal conversation with anyone, anywhere in the world, no matter what language they speak.
That would be incredible. But, okay, with all this talk about giant AIs, how powerful they could be, is there a point where bigger isn't better? Like, I get that these models are already super complex, but is there a limit to how big they can get, how much they can actually learn?
That is the million-dollar question, isn't it?
Yeah.
And it's something researchers are trying to figure out right now. It's totally possible that at some point we hit diminishing returns, where just adding more parameters, more size to a model, it doesn't actually make that much of a difference. Plus, there are always practical limits to think about too, like how much data is out there, how much computing power do we actually have access to?
So it's not just about bigger AIs, it's about
Yeah.
smarter ones, right? Finding better ways to train them, optimize them, even if they don't have billions of parameters.
100%. And that's where it gets really interesting. We're seeing some cool stuff happening with like transfer learning, where you take a model trained on one task and you can adapt it to do a different but kind of related task without needing to start from scratch.
So it's like if you teach an AI how to ride a bike, it doesn't also have to relearn how to walk, right?
Exactly. And that has huge implications for making AI more accessible, more useful for a lot more problems.
This has been honestly kind of mind-blowing to really dive into this world of GPipe and these giant AIs. We've covered a ton, from like the technical stuff of how they're trained to what this could all mean for the future.
It's been a pleasure exploring it with you. Hopefully our listeners have a better sense of, just how much potential there is in this field. It's really moving fast.
Yeah, for sure. And I think if there's one thing I hope people take away from this, it's that, the world of AI, it's full of possibilities. We're really pushing the boundaries of what's possible here. Who know, no WS, what amazing stuff we'll discover, even just in the next few years.
Exactly. And to everyone listening, keep asking those questions. Keep learning. The future of AI, it's in your hands.